Okay, I think we should get started. I don't want to be late today. It's quite, there are quite a number of topics that we will have to cover. Part of it was from the last lecture on the DPM, right? And another part is the latent diffusion model, which is the original proposal for stable diffusion, which you can say that it is the stepping stone, the milestone of generative AI. That back then when it came out, it kind of changed what we see in generative AI entirely. So we will look at that, right? And the topic that we will cover will include the DPM and all the related issues, all the related ideas that are related that are in the latent diffusion model and the implementation of the stable diffusion as a specialized case for latent diffusion. Okay, let's start. All right. So continuing from last lecture, I think I should show you this first. Um, Actually, from the last lecture, you may have already seen the notebook that I implemented, but I'm going to show that to you here. This is the DDPM on CIFAR 10. I trained it according to the original paper, right, which requires 800,000 steps in total. Okay, so it takes about 2 days entirely to train the whole thing on the CIFAR 10 dataset here. And these are the same one. We have the diffusion model, Gaussian diffusion, contains Q samples to sample Qt given Q0 and predict X0 from epsilon and P sample, which reverse the step, or reverse the xt minus 1 out of that. Right, and then this is the forward process by injecting the noise, right, and then train, injecting the noise in, and train the model to remember the noise pattern to predict the noise. And the model we are talking about is the UNet. UNet contain the residual block, attention block, and the down sample and up sample. So this is the UNet. It contains the encoder part. The encoder part will down sample the data to lower rate in the middle, which you have the residual block and attention block, and the decoder here, which will upsample the data until you have the same size as the image, input image. Okay, and this for UNet. UNet forward would be passing through all the block, and this is the creation of UNet. And then this is to make the learning process to be exponential moving average. And then the training part. This is training on 4090. You cannot do this on Colab except if you you are on the Colab Pro, which you can utilize the compute, but it takes quite some time to run this. Okay, this is the training part. The training part, we have injecting the noise in just like last time, and then perform Q sample from x0 to xt, and then randomly injecting the noise, right, on the step that we specify, and then learn to predict the noise and optimize the step. And this is 800,000 iteration. Take quite some time. Have to restart the process multiple times to finish this. Once done, this is the load from the checkpoint, and then there are 35 million parameters, and these are the grid of generated samples. It looks quite nice here. And this is the visualization of the reverse process from the noise, and then we see different level of subjection to the noise in and the denoising process. Right? Once at the end, we have like the image that we obtained. And this is the FID evaluation. Took quite some time to run the whole thing. The original paper has the value of FID to be around 3. I got around 7. Probably may need to do fine tuning and also perform other things more. Okay, this is the DDPM. Takes quite some time in um, for the inference and for the learning process. So especially in the inference part, it takes quite some time. I think one iteration required 60 seconds or so to do the inference. So we will do it differently this time. Okay, so we are going to look at a way that you can use math to help reduce dependency in the inferencing process. Once you reduce that, then you allow the model to not to have to follow the DDPM step every time. It can jump and use smaller steps in order to perform inferencing and having similar qualities in terms of the generated output. Okay, this is the recap of the last time DDPM. In order to train the model, you have data sample, add noise, then you have noisy data in multiple steps. And in each of these steps, you would have the time embedding and the XT that you add to sample. And so you know noise, right? You know the noise here. So what you are training the network to do is to use noisy data and time embedding to predict the noise, right, by optimizing the square error between the predicted noise and the actual noise. And during the reverse process or inferencing process, you start with pure noise and then assume that this is the end state, the T state. And then for each of that, you would have xt and t, the time of actually it's like the last step, right? And then we will use the same network, flip it, and then predict the noise and use the predicted noise to improve the starting pure noise to become x of t minus 1. And then repeat the process again. The improvement here is done through the sampling of this distribution. We know that the correction will come from the correction, the mu theta xt of t here, then mu of the new distribution will be xt, the previous pure noise, minus the predicted noise. So basically, this is the reduction or return, reverse the process, so that you generally have this one as the estimated value for the generated data, and then treat this as the mean of the new distribution. Then draw from that distribution of using the mean value entire exactly. Then you can have um, the reversed one step reversed pure noise, and then from this one it will be fetched back to start here again, and repeat the process multiple times until you get x0, right, which is supposed to be the denoised version of the data. So that's what we see in examples earlier as well for the DDPM. The problem with DDPM is that because it is a Markov process, right? What does it mean by Markov process? For the Markov process, you have the current output or the current step depends on the previous steps. This is the probability of xt minus 1 given xt, right? The reverse part. But because it depends on the previous step, you need to generate the previous step first. Generation require to run full reversal chain. Right? If you have t equal 1,000, then it means it has to pass through unit 1,000 times. So suppose that one iteration require 100 milliseconds for passing through the unit. That means 100 seconds, right? Time 1,000. Time 1,000. Uh, so 10 would be, so 100 seconds per one image is like a minute and a half, right, for an image, which is very slow, very, very slow. So it makes generation in real time, the DDPM makes generation real time impractical. So there is a better way, which is to make it non-Markovian. Okay, so the bottleneck here is that each step depends on previous step because of the Markov properties, which require every intermediate xt to be inferences, right? And you cannot skip or stride over time. Um, but for DDIM, the training loss will not be Markovian process. DDIM was proposed in this DDIM, Denoising Diffusion Implicit Models, the paper by Song and his colleagues in 2020, and also in the ICLR papers 21, Song 21, score-based generative models through stochastic differential equation. You can take a look at both. The first one would be the paper. The second one is the GitHub that contain the scoring and evaluation of the method. This is very recent if you think about on the grand scale of things, right? We are talking about the technique that has only been created 5 years ago. Just 5 years ago, think about that, right? A paper just published in a conference 5 years ago, but it has now been in parts of a lot of generative AI technologies that we see out there. Um, and you will see that the pace of development has become really, really fast, and there are quite a lot of contributions throughout the year. I would provide the link for you to look further into that. Okay, so how do we do that? How do we make DDPM non-Markovian? Okay, so the idea of DDIM, the implicit model, is that it keeps the same trended model. You still have the same model, the model that will predict the errors. Okay, so it is trained through the same process. We use the same model. What will be different will be the thing that will be different is the sampling, right? The sampling procedure or the inference process. That will be the different one. Okay, that is not relying on um, the the earlier iterations so much, so to make it work. Okay, so the process is the forward process in this case is generalized to the family of non-Markovian process. How do we make it non-Markovian? We must make it in such a way that it doesn't depends on the previous state. Okay, when you hear the word Markov, the concept of Markov or the Markov chain is that the next state depends on the current state. The next that means in this case the next set of noise depend on the next set of like inferencing of x10 depends on x11. So that's for the DPM. But instead of that, we will treat the Q sampling, the inferencing one, to be this instead. So you use it that Q of x of t minus 1, instead of depending on the xt, now it will depend on x0, the original image that is supposed to be. Okay, and then it make the output here to not depends on xt, but it would depend on the predicted x0. That means the reverse step has to contain x0 prediction. Oh, okay. So it's not just noise. It also has to predict x0. Given xt, you predict x0. Right? This is the predicted x0 given xt. These predictions come from xt, come from the current noise minus and the predicted errors. Right? This is the predicted errors, e theta of xt and t. Okay. So we are predicting x0 from xt, and then what we subtract out are the predicted noise and scale with alpha t. And xt minus 1 and xt minus 1 also comes from x0 in the above, right? If we were to arrange equations, we will have that xt minus 1 or the value that we want to inference comes from x0 of xt minus 1, the predicted x0 plus the noise, right? This is the noise part. The noise part, the predicted noise, and the scale that are related to deterministic process. You remember the alpha that we multiplied last time, and sigma square here, which denotes variation of the noise. This is the variation, and the noise at time t. This is predicted noise. Okay, so what it makes the inference here on specific step to be depend on x0. But how are we going to do that? We will look at a way to do so. Sigma t here, I control the noise injection from each step. So it means that in this term, sigma control the injection of the additional noise is epsilon t. So at the step t, if the sigma becomes sigma t, certain value, then you get the DDPM to be full stochasticity. If you remember, in the DDPM, at each iteration, we will add just a small amount of noise, right, so that it has a certain stochastic properties in that. And DDIM here will set sigma to 0. Once sigma is set to 0, you have the above equation. And the above equation doesn't contain the stochastic elements. It makes the inferencing become fully deterministic. That means you get same image every time. If you get you give it with a specific set of initial noise, you get the same image. Enables latent interpolation inversion later on with this, because it doesn't have these terms, right? This term, this term, the sigma term here, right? The sigma that are related to variability. So because now doesn't depends on the previous step. right? xt depends on the predicted x0 from where xt is -1 um, depends on predicted x0 given xt -1 and the predicted noise. So starting from xt at the end, instead of um, instead of going uh, going 1,000 steps to x0, we can have only 5 steps to x800, 600, 400, 200, and then x0. Right? We can have the step that is not depending on the previous one by having this prediction function to predict the kind of the x0 at the origin. Right. So the process would be choose S, choose the step, and then yep, build the subsequent tau, which means the step function here, on how fast you would want the step to go through, and then run the DIM update using alpha and then tau index that you have here. Okay, we will look at the code and the inversion of the DDIM afterward. So comparing the two properties, you have DDPM, which depends on the previous state to be the Markov chain. DDIM is non-Markovian. You have around 1,000 steps, and then this is like 10 to 50. We will see that there are effects there when you use the DDAM. This is stochastic. This is deterministic, right? And then also um, DDPM, so it doesn't require returning. You use the same model. Um, you also have the DAM latent inversion, which we'll look at step next on the next page. And image quality comparing to one another. This is high, so if you have a step large enough, but the speed is a lot faster. Okay, what is DDIM inversion? And in order to do the forward and inverse. The ODE, you have now the difference equation because you have the change of the next step, right? So it means that you can run forward by encoding the real image x0 into noise. This is x0 that you can this would be enable you to do image editing without retraining later on as well. So in this case, we have the prediction of x0, and this is a forward process, encode the image to noise. So you have x0, and this is the noise prediction of x at that iteration. That has to be trained in the model. The forward process is to get X at the next step, right, depending on what you start with. So adding noise of that step to original image will give you image of at that iteration. For the reverse or the generative part, which will reconstruct image from noise, will be the prediction, right? And then you have the error prediction come from here as well. Okay, so for the DIM, it is faster, and it open the pathway to later on that you see in the latent model as well. So application of the DDIM is that you can now do image editing with text guidance. How is that? Because you have a way to map a certain latent to a certain image. This is the way to map. You can encode image to noise. Say you can encode an image of horse to noise of horse. Then you can also combine it, reconstruct it back, right? That's the reverse process. So it allows you to do editing with text guidance in a way, do the style transfer, and it actually opened up quite a large research in generation. Um, not about the model itself, but about style transfer, about interpolating the latent. If you want to try on, you can try on with the code later on by mixing the latent together, mixing the noise together, and see what would be the generation result if you were to mix the latent together. Maybe you get something interesting, right? And it also become consistent for image to image translation. Um, okay, so caveats for DDIM is that inversion is approximate. So inversion, it at best would be DDPM. Okay, it's faster, but the highest quality would be in form of DDPM. Um, classifier free introduce CFG classifier free guidance, introduce reconstruction error, and there's now text inversion fixed. There are other papers that we'll discuss. You can take a look at it later on. But for now, let's look at here. This is the comparison between the two. I already run on my computer here. Okay. This is DDIM, DDPM by whole, right? 1,000 step, DDPM by whole, and DDIM by song. This is the math, the prediction, and a prediction of X and prediction of error. Okay, I'm not going to run it again. I just want to show you here. I think I also have the time lock to show you the demonstration. Some configuration of the model. It still use the checkpoint DDPM latest that is trended earlier for CIFAR 10. Then the unit architecture. You got the rest block, attention block, the same thing as the last time, the unit. Okay, and then load the model weight to the unit. Here, load the model weight to the unit. And then in terms of DDIM, we would have the step tau set to S step. Okay. It is new 0, this is fully deterministic. New equal 1, it is DDPM like. Okay, this is the function, the share helper function to predict x0. Okay, this is square root AB and square root 1 MB, square root of square root alpha cumulative product of x and of t and xt. Okay, and we have to look at the function, should be down there. Okay, here alpha cumulative product, which is square root of alpha cumulative product. The square root of this alpha cumulative product come from alpha cumulative product here. And alpha cumulative product is the cumulative product of alpha. So if you remember last time, we also have something like this. It's the way that you determine the current version of the noise, right? Calculate cumulative product of alpha. So this is for this self alpha t and xt, and then you have square root 1 MB, square root 1 MB. This would be the 1 minus alpha cumulative product. We should look at the equation instead. 1 minus alpha cumulative product here, this part. This is a square root cumulative product. This would multiply with x hat, and this would multiply with the prediction of errors. Okay, multiply epsilon, and you have xt here, coming here, the square root. The DDPM, like last time, you have the DDIM sample, which useless iteration. Okay, you have yeah, and okay, I heard If you have question, please ask, or you can type in the chat. Yeah.
เราค้างอยู่แป๊บนึงได้ไหมเดี๋ยวก่อนกำลังจะเสร็จอยู่แล้วหายไปเลย
Right. Not us. Okay. So in this iterate, the focus would be in the iterators, because this part will be the part that you iterate through denoising process. Okay. First, you get the time step, and then you have the epsilon, right? Come from the model of x and t. Remember, this predict the error. And then and you have x prediction, x0 prediction, comes from the equation. Actually, you look at slide, there will be the prediction of x0 in the slide as well. Should be in the page non-Markov difference process. Xt minus 1 minus alpha epsilon divided by square root something. And this is the thing, the prediction of x0. And then for this, you can do the DDIM noise schedule. Using x0 to estimate the current x of that step, which is the square root of AB at the next step, x0 predicted, and the part that is random, and this is sigma time noise. Noise come from random sampling. If sigma is 0, then you have DDIM. Okay, and sigma is here from it is from this, from the eta, the control of the noise process. Okay, I think we set it to DDIM, so initially it is it was set to 0, but we have the comparison later on. Okay, so this is the implementation from the math. You can see that it contains x0 prediction. It contains still contains the same thing, calculating the AB, the alpha, and it contains each part of the equation, but the calculation is done deterministically, except the noise part here. If ETA is less than or equal to 0, then it becomes 0. So that makes sigma 0 in a way here. And this as well becomes 0. Then you got quite deterministic, just the AB next time and x0 to be the DDIM. Okay. So comparing to DDPM, this is DDPM 1000. Let's look at the overall quality of the generation, and then compare to, say, the car here, and compare to DDIM 10. You see quite a drop of quality in the DDIM 10, but if we were to look at, say, DDIM 100, then it becomes a lot better. Right? The car becomes a lot better comparing this one to the car here. Start from, I think, 25, 50. It looks like the real cars. In terms of the drop of the qualities, you see it less and less. Here are the overall DDPM and DDIM. Right? So you can see the change in the quality, especially in some of the detail. In terms of the speed, this is one of the most important thing. For this is the batch type 16, DDPM took 6 seconds to generate, while DDIM 50 took only 32 milliseconds. Okay, 320 milliseconds, right? 0.32 seconds. So a lot faster. 20x faster than the DPM, with the quality quite okay to a certain level that you can see, right? Comparing from the DPM to the DDIM, you can see the difference there. Okay. Yeah. So that is DDIM. Any question that you would like to ask first? I don't have my camera with me at home today, so only have microphone on the new computer. So even though I'm not turning on the camera, but I'm here. Do you have any question first about DDIM? As you can see, the core concept of DDIM is in this equation, the DDIM reverse step, right? That calculate x0 here. And also the next one, that is to estimate x at certain iteration. You have x0 predicted from xt minus 1. And then actually, I think this should be xt though. I might make mistake here. It doesn't make sense if you predict xt minus 1 and then yeah, I think it should be xt, not xt minus 1. It should be the predicted x0 from that iteration, from iteration xt. And then you have the estimated noise to guide the image to like skip 200 steps to that point, and then keep doing that 200, another 200, another 200, then it will finally reach 1,000, right? Take larger step in a way, right? With this equation, and that's DDIM, right? The implicit model. And that is, you have the model to predict x0 beside having just the model that predict the noise, right? So that's what we look at here. So once you know this, the DDIM, you can see the change, the evolution of the process from the DPM, which require gradually decreasing the temperature, right? The T from 1000 to 1 to 0, right? While for DDIM, you choose a larger step and then jump by approximating the process so that it doesn't rely on the previous step, right? And then make a larger step. So it allows you to do that. The DDIM has become the standard sample in a lot of modern diffusion pipeline that include stable diffusion as well. There is variants of DDIM like PNDM, DPM, DPM++, you see later, and DDIM new here, ETA here. That okay, so there are quite a number of variants. You can look at the detail of each step if you want to understand that. The next one, we will go to LDM and stable diffusion, and also look at the stable diffusion XL. Okay, any question about DDIM before we move on? I'm not sure if I have uploaded because I think I haven't uploaded the version, right? The version, the DDIM version yet. I will do that afterward. Okay. Right, then let's look further. Right, the next part will be the interesting one. From 2022 to today, the models that we are still use are still stable diffusion with a larger model, more sophisticated inferencing and training process. And to be more complicated, it's now incorporate all the types of Latin into the same model as well. Not just image, but you have image, video, text combined to become multimodal in a way. So what you see in the diffusion in the DPM, in the DDIM, diffusion model that we see earlier, they are what is called pixel space diffusions. Okay, so we are at this point. Right? We want to learn about that. So what is this? The pixel space diffusion is a diffusion model that you perform diffusions on pixel. Okay, let me go back a few slides back here. You can see that the prediction of the noise process here is done through the visual level. You take the visual data, the X data, add it with noise, and then predict the noise at the pixel level. Okay, this is called a pixel space model using pixel for noise prediction, for the path prediction. But it fails. Why is that? We will move on. The reason, just go to the reason. The reason for it to fail is that it is hard to generalize. Just like in GAN and when you see autoencoder. In VAE, in variational autoencoder, you have a variable, right, that you can control. Once you control the variable in the VAE, it allows you to mix different latent together, interpolate them, right, to get the meaning and then generate it out. In GAN, it worked at the pixel level. It worked at the visual level. Okay, and then that's the same as this diffusion as well. Okay, diffusion model here work on pixel space, but the latent diffusion and stable diffusion will work on the latent space. Okay, so that means the difference is that we will combine the concept of autoencoder together with diffusion. So starting from the image, right, you suppose that you already have the trained autoencoder. Starting from the image, we will compress the image to the latent. Like compare the image through the encoder to get the latent. And then from the latent, we will perform DDIM on the latent, right, on this latent directly, not on the image. Okay. And then it means that we will do the DDIM to denoise the latent. Right? In the forward process, it would be adding noise and then predict the noise at the latent space. In the reverse process, it will be predict the noise, remove the noise in the reverse process, just like what we learned in the previous class. And then once we have the predicted version, then it passed through decoder to get the image. Okay, it looks like this. Start from this. Let's think about it in the what for this one in a generative way first, right? Suppose that we already have the model trained. You okay, so you already have the model trained. No, it's the same thing. This is a forward process. This is the reverse process. So in the forward process, you have image, right? The image here. The image will have to be encoded to C. Instead of adding the noise directly, it will be encoded first to the latent vector. Then the latent vector will be added with the noise, right? Just the same thing that we did earlier. Added with the noise and then train the noise prediction part, just like the earlier one, so that you get the noisy vector and then use it to train the model. In the reverse process, we start with the noisy vector and then pass through the UNet to the noise. It will predict the noise out, and then we can use it to remove from the CT to get the original version, and then use decoder to decode it back. Now, conditioning come in form of either text, image, or authors. It will come through the UNet and concatenate with CT as part of the latent, and then inject to each layer in the UNet as well. in terms of conditioning. And then still, it will still perform prediction of the noise. And then from that noise prediction, you use it to gradually adapt CT back to C and then perform decoding. Right? So that's the process of latent diffusion model. You can see that the difference from the latent diffusion and the previous diffusion model is only in terms of you have encoder and decoder. Now you have a type of autoencoder that is encapsulate, right? Autoencoder encapsulate the latent, the diffusion process to make it work at the latent domain than the pixel domain. Okay. All right. So comparing to in terms of resolution. Okay. So CIFAR 10 is what I tested and show you. The resolution is 64 by 64. Okay. Comparing to the standard model that is done by author here. This is lowest preview in Windows. For stable diffusion, default one is 512 and by 512. This is 64 time from baseline. If the pixel is larger, you have a lot more pixel. This is to show you that if we were to perform noise prediction at the pixel level, we would need to predict 4 million value of noise for each iteration, which is huge, right? You don't want to do that, right? It requires 4 more pixels, 4 times more memory for learning the activation. Okay, so and also self attention require for this spatial region is ON square. That means pixel-based DDIM of 512 will require 10 gigabyte of VRAM per inference, just per inference to get in full precision, which is quite a lot. You don't want to do that. That means the reason that Rombach came out with the technique to do this is one of the things is to solve the problem of scaling. Right? So you can train the model to train the learning process to be at the latent vector, which is fixed in a way. Okay. So comparing to DDPM, unit parameter is 100,000. Sorry. Oh. Well, seems like I'm not well throughout the semester this semester. Okay. Without LDM, you can see the scaling of the VRAM from 1 gigabyte to 8 to 24 to 48, and the time of generation per image of each of these. This is not okay, right? Comparing to LDM, that we have 8x spatial reduction in terms of dimension of the representation. Okay, so and it represents in the latent domain rather than the pixel domain. For autoencoders, you can just train it earlier. You can train the autoencoder before using it with the stable diffusion. That's usually the way to do. So this is more practical. Self-attention is ON square, depending on the n is height and width here, because it has QKV in multiplying one another. It's quite a lot. Matrix multiplication. Yeah, doing latent is definitely better for sure. Okay. Comparing this to previous approach, diffusion expensive. Right? The diffusion that we learned earlier, generate low resolution, then upsample, right? What we see earlier in the unit upsample. You can cascade them together to make it able to refine a number of iterations, but they will be expensive to train and run. The first one here. For GAN is fast but unstable. There's mode collapse that there's training instability, and there's also mode collapse there. But very nice idea in game theory, right? The idea of style GAN that you learned it earlier, of you have a type of adversarial training, right? For vector quantization and VE or VAE, or variable autoencoder that you learned earlier. These are quite good, actually, still applicable to what you will see in Stable Diffusion, because you can have variable autoencoder adding to perform latent compression and then performing diffusion on the latent space. LDM, this lecture, this will more focus on the compressed latent vector. And then you have one model, have flexible condition. It's quite practical. You can test it. There's already well resources that are built and you can test. I just pull one and then show you here, but there are quite a number of them. Especially in nowadays, you can test it with the Stable Diffusion XL, which is very high quality. We'll talk about that later on. I have some example as well. Okay. So the key insight for Stable Diffusion is that it separates compression from generation. The compression part is the part that relate to autoencoder. It separates the compression from the generation part, which is diffusion model. So you can think of this as containing two parts. The autoencoder part trained it once, frozen, and then used for compression and used for decompression, decode and encode. So that means this can even be shared by researcher. There are quite a number of VAE, quite good VAE that you can use. This would remove high frequency detail. It would encode data, structural data into the vector. Okay, and then you have the generative part. This generative part would learn data distribution of the latent space, and you use DDIM sampling like 20, 50 step versus 1000. Okay, and then you can have text image conditioning using cross attention, attach it, and then make it condition. Okay, so it divided to two parts. It worked like this because it has separate purpose. Although encoder would handle the texture, the encode of data to the latent space, while diffusion model handle high detail, which comes from revising the detail of the latent vector. So you can think of autoencoder as the part that would take care of the structure of the image, and then the part that about the detail will be taken care of by diffusion. Okay, let's move on further. You will see the detail later on anyway. So LDM perform better than the DPM for sure. Okay, the pipeline looks like this. You have encoder, and then you have diffusion, and then you have decoder. Then in this way, you also have condition that you can subject to. During the training, it is the same thing as the earlier diffusion. During the training, you add noise to the latency, right? Add noise to the latencies, predict noise with UNet, similar to in normal diffusion model. Autoencoder is already pre-trained. Right? You can use the existing autoencoder or the one that we trained it in previous lecture like that. We will train it, the autoencoder, or the autoencoder is frozen, means we are not going to train it any further. Then for the inference step, right, we use the DDIM that we mentioned earlier, starting from the sample CT, and then the noise 50 step decode, right? And then for this, we can also do the condition by injecting to the unit every step using cross attention. So this is the image. This is the link. You can click at this link to go to that. All right. So here's our condition. That means during training, during training of the UNet, you also need to subject the UNet with the condition as well. That means you need to have annotation of the image and then add to the unit training. So it sounds easy, but the hardest part would be annotation that has to explain the image, the component in the image. And then during training, you can then encode the data to diffusion here, add in noise, and then use the noise, which is xt, and the time t, and you have the condition to train the unit. Right? You can train the unit to predict the noise, and then when using it, we use it together with the condition, the noise, to condition the generated here to be just like what we have here, starting from random noise, and then you have here to inject to each step, so that supposedly, see here, this is like random noise, and we put here horse, then at the end, it should be horse, right? So because of the condition that we put into the model. So slight prediction to change noise to the noise of horse, and then the latent will be converted using decoder to the image to be the horse one. This is the concept, right? It's similar to diffusion model we learned it earlier in the last time. This is a paper from Rombach in CVPR 2022. If you are interested in that, you can just go to download. This is one of the, well, if transformer is one of the revolutionary one, this one would be the starting point of today image generation, right? Because before it's okay, you kind of have diffusion model that you see in whole work on and song, and but this is like the step that you have. So it's not transformer comparison. This should be the comparison to when we use word embedding, right? Right. So similar level to that. It is kind of create. Um, it would be like the first time that you can generate image up to this scale using PC, using normal computer with the pre-trained model. Okay, and it created quite a stir and quite a controversy as well. Okay, let's look at each part first. I'm going to go through really fast for the autoencoder. We already we have already covered this in the previous lectures. So to remind you, autoencoders contains encoder and decoder, right? The objective is to compress the image into the latent space and then enhance the data from the latent space back to predicted version. Training would be that the two are the same, right? So you should have like high fidelity reconstruction, and you should have like well structured latent space that differ from that one type differ from another types, right? So this is AE. For the VAE, you have here representation of the data into the mean and standard deviation, and then generation come from sampling of the latent space. This is VAE. So the loss function will then become the reconstruction loss, the MSE, and the KL divergence loss, which is regularization of the distribution, so that the data should be well separated. This is VAE. This is each part of the loss function, the KL divergence, right? That is the distribution should be its own mode. I'm going to go through this. This is the sampling effect. Never mind. We are going to look at the compression here. This part is the perceptual loss or the reconstruction loss in the loss function. So combine all, you have reconstruction loss, KL divergence. Actually, some of these also has like adversarial and perceptual loss. But in any case, optimize the autoencoder, you get a network that allow you to compress the image to latent vector, latent space. And you have decoder that allow you to decompress it out. Right? So those are the two things that we want, encoder and decoder architecture. Like we will have these two, like the one that receive input and then compress it to the latency, and then the one that you get from the latency and then upsample it to the output. I have the two together. Okay, so this is the one that we are going to use. All right, let's then look at the diffusion in the latent space. In the pixel base, input is real value, the size of 512 to 512 to 3, right? And the unit have to process 512 times 512 feature maps. While in the latent LDM here, you have the C, the noise vector, the latent vector to be real value of 64 times 64 times 4, right? And the unit would be 64 times 64. Comparing number of nodes there, they are quite different, right? Number in terms of memory, in terms of the time to process, quite different. Okay, and the diffusion, forward and reverse. Forward diffusion, we want Q of CT given CT minus 1 here. This is the DDPM though. If it is the DDIM, then you have like the XDX0 or instead in that, or C0 instead. But this is just to refer to DDPM. This is from normal distribution. You get the mean to be CT minus 1 and variation beta T. And reverse process would be the P sampling, like P theta sampling. You get CT minus 1 given CT and learn through noise prediction and then subtract it out. You get DDIM to accelerate things. That's it, actually. We can just jump to the code. The error here for the loss function of LDM is the error, the difference in error. This is the predicted error and the predicted noise and the real noise that you generated, okay, from the latent space. And then we will try to optimize this. Right, the backbone is UNet. We already see UNet in diffusion earlier. UNet is originally used in 2015 for biomedical image segmentation. You have encoder part, downsample, you have decoder part, upsample. You have skip connection to preserve the fine grain and also for the gradient to fall back. Okay. So in diffusion, this would map the noise CT to predict the noise epsilon here. Okay. I think it's all right. Okay. UNet building blocks contain ResNet, self-attention, and the cross-attention block. Let's look at this. We have the input part. It contains the ResNet convolution and the self-attention, capture long-range prependency, and the cross-attention to include the condition from text. Let's look at the input here, the contrastive language, right? The context encoder. Context encoder will be added here. You can see the block here to the cross-attention block for each of these during the upsampling. And also at the end as well, after predicted, to go through the decoder later on. Okay. And initially this is time, right? Adding time to this one. And the self-attention in orange, and you have ResNet block in blue, and cross-attention. This is for each up and down block to capture different part of the conditions. Okay, and with this, you can add in different types of context. You can add in different type of latent to perform condition. It can be class label. just the label. It can be text, which Stable Diffusion used to form text to image. It can be image guided generation, image to image, right, by changing clip to clip image encoder to perform visual embedding and perform cross attention. Then you have reference image and then the generated one. Or you can combine both as well. You can have segmentation map and then allow it to generate from those segmentation map. Okay, those are the conditions that can be added. For the text conditioning, suppose that we use text. It's called CLIP, the contrastive language image pre-training here. CLIP is trained on 400 M image text pair. So it is trained on based on the pair between image and the text. So from the text, right, and after tokenization, then you have the token embedding. Think about it as the embedding of the text that you have, and then the embedding will be fetched to the unit through cross attention KV. Stable diffusion, it is trained for stable diffusion, it's trained use VITL 14 specific clip here. And then so it contains 77 tokens and a specific embedding size. So different model of stable diffusion will use different clip, right? So this is SD1 and V1 and V2 use one thing. For SD3 use T5. You can get longer context. For SDXL, it's switched to use open clip here. And once you got token embedding, the token embedding will be injecting to the text through unit by add to the cross attention part. Okay. So this is the part that let's look back to this image again. Let me go back a little bit further. Okay, here, this one. You can see that this is the concatenate, right? It show. So it will concatenate with the CT. Think about it as subjecting to the noise to this. So that this input part will be concatenated with the condition. And the KV as well, the QKV here will be subjected to the condition. How does that work? Okay, you have query, right, and key and value in transformer. So Q would learn the attention here of the Q and K and V is the dot product of K and Q, right? Query and key together, and then softmax is to become a type of mass and then multiply by V. Okay. So K and V here will be linear projection of token embedding for the K and V. So the result here would be the attention of the text related to the image that is trained. Okay, so if you think about it this way, it's like this work like word to vec that we have previously when we work with deep learning model, but it converted the token to embedding through, and then this will be used as condition. Okay, as condition to the training process, right? So beside this, besides just the text that's used subject in the cross attention, there is the classifier free guidance that's used in training. So what is this? This is the drop of condition C. That is the CFG is used to represent the predicted noise. You have the predicted noise of C at the iteration T and the certain condition here. You can have the this to be the unconditional prediction. That is, there is no prior distribution, no latter part here. So you have only W time the prediction of the noise, or you can have the guided text C and also have you have guided text here in positive part. You can have the negative part in here, right, to act as the the subtraction of the noise from this. So in a way, the predicted noise will represent, the predicted noise here will represent the positive prediction of the noise from your positive prompt. And the the latter part here will represent the negative noise, right? The negative noise from the negative prompt. Okay. So now you have the guidance, and the guidance depends on W here. It depends on W. Stable diffusion use this around 8. That is, you have the base noise, and then you have the guidance from the condition. The difference here would be this doesn't have C, it doesn't have condition, but you kind of impose the condition into the base noise. So combined, well, the training objective come from noise optimization. Center in the difference between this injected noise and the predicted noise. The predicted noise depends on the current value of the noise of this noisy image, depends on the value of t each step. If it's t1000, you got pure noise. T0, you got pure image. And this condition, the tau theta condition, which depends on the condition. So the predicted noise depends on that. And what we try to optimize is to optimize the prediction of noise here. This is domain-specific condition encoder from CLIP. Okay. The training of the process here is done by first pre-train encoder, right? Pre-train encoder using unstructured data, just pre-train it. Then freeze encoder and decoder. And then this would also extract latent of our training image. Then train the unit of the latency condition on this, like on 5B. This is for stable diffusion. And then fine-tune on curated high-quality subset for aesthetic subset. This is the way that the stable diffusion work, right? And how it involved with representing the noise here. The next part will be this. So from the latent diffusion model, there's no demonstration specific to that. We will just look at stable diffusion, look at stable diffusion example, look at stable diffusion XL, and look at stable diffusion XL examples. Okay, because stable diffusion is essentially LDM that you see earlier, work on latent space, plus clip, plus lie-on scaling, the data set. You have LDM, you have clip with L14, you have specific unit, and you have the data set, lie-on 5B, image text pair. These are trained on 256 A100 for 150,000 steps. I don't have enough money to do that. So I'm going to just do the inferencing. Right? The training is not here. Even though I have like 2 A100, I probably cannot be able to train. But you can try fine tuning or creating the adapter. That's fine, right? Fine tuning, LoRa training, those doesn't really require a lot of well, it requires quite a bit of computational power, but not as much. Okay. Okay, so the latence shape, 64 times 64 times 4, 512 times 512, attention head, 8 head, dimension of 64. DDIM of 2050. This is the training data set, the one that used for train the model and for fine tune further. And the unit channel, cross attention dimension, the CFG value W, and the licenses used. You can go to this website to get the GitHub. I already have the code that I think I already shared, if I'm not mistaken. Yeah, I already shared this version of for Stable Diffusion to everyone to play with. Right? It's called the data from GitHub. Yeah. The architecture looks like this. You have a clip text encoder, which encode the text to the embedding and the tokens. And then this is then injected to your UNet. You have decoder to put it out. This inferencing step by step here start by tokenize the prompt. You have a cat on a mat tokenizes as this base pair token. And then using clip transformer to encode the encode to token embedding of 77 times 768. And this is for the positive value. You can encode fee as well for CFG if you have negative as well. And then sample the latent noise from normal distribution as a seed that we have. Then perform the DDIM, start from CT, and then predict the noise, adjust the noise, compute CT minus 1, apply CFG at each step. You can have the error, the guided error as the unconditional and the conditional one, right? And you can see this is a lot type. This is like an interpolation from an unconditional one, predicted unconditional one to the conditional one. And then finally decode the latent. You have X hat using autoencoder decoder, right, to upsampling it. And then finally, you can have filter, add in watermark as in Gemini, performing non-safe for work, NSW filter, if you want to add filter at the end, or performing upscaling using image processing and further. This is processing process. Okay. So that's so you can see that I put here as the encode of the fee, right, to perform the unconditional and the conditional one. But as I said, you can also put in the negative part, which you replace the fee with the negative. You replace the fee with the negative to have the contrastive difference of the noise prediction. So basically, instead of using unconditional noise, you use the noise from the negative as the base, and then compute the deviation from the negative to be the estimated or the predicted conditional noise to adjust the noise to perform the denoising further in stable diffusion. So the steps are the same, more or less. You have input, and then the input you have latent at the step T, CT, and then you in the CT it predict the noise, and the noise used to adjust the value to the CT minus 1 from the predicted version. Okay, then you get the latent for the next step, and then keep doing this further and further. Okay, and then you have different types of solver, which we'll look at later on. You don't have to stick with, because when you perform stable diffusion, there are multiple types of solver, multiple type of noise scheduler. The way that you subject the latent to the noise, there's a scheduler. Right? You can use the DDPM, DDIM, or some other like Euler and DPM solver plus and later on, which we'll talk about at this stage. This is the sampling scheduler, or sometimes it's called noise scheduler. These are for adjusting the noise. So you can think of this as a process of just like an annealing process. Like you have data that contains a lot of entropy. Those are the noise data. And then you want to gradually remove the noise, right? Remove the entropy out step by step. Okay. If you perform it too fast, you might end up with local optimum, right? Not the best one. If you perform it too slow, it might take a long time. It might be slow. So these are the noise scheduler, right? What we saw earlier are DDPM and DDIM. Right? The default one for stable diffusion is this one, DPM solver plus plus. We will look at how it works later on. And there's still DDIM here, the standard ODE, deterministic ODE. And as you can see, it's fast, good, quite and deterministic few step. DPM solver plus plus, also deterministic, quality speed very fast as well. And there are some stochastic, right? Euler and Chestro, the DPM here are stochastic. The idea here for the DPM solver, this is the best one used in modern stable diffusion UI. DDIM, this is simple deterministic, what we learned earlier. Euler and Chestro add stochasticity in that. So let's look at each examples here. So the sampling scheduler relate to how fast you want noise prediction to impact the noisy image, how fast you want the denoising process to go, right? There is a paper here that contains all of these I mentioned, quite a good overview. So these are some denotation. You got noise schedule, the alpha t that you have. You got latent CT, predicted noise epsilon theta of the CT at time t, and the previous latent CT minus 1. Okay. So for the deterministic solver like the DIM, right, we get CT, CT minus 1 here, from CT minus the predicted noise. Okay. This is predicted clean image, the first part. This is the prediction of C0 or X0 earlier. And the noise part to change the direction of the noise. So this is the second part. Okay. So it's attempt to clean parts, clean the flow of the image. So this CT minus 1 come from the clean image plus some noise direction. So there isn't any sampling happening here. Right? All of these are stochastic value, deterministic value. The alpha t minus 1 is all deterministic prediction from neural network. The stochastic, this stochastic differential equation solver, the Euler and Chestro, Euler A. The Euler update step, CT star, this is CT, and then you have the predicted noise. In this, it contains two parts. The first part is the part that contains the predicted noise, but this part for Euler A, it contains the sigma t here as well, and the sigma and Chestro. Both of these are noise sampling. So it has to sample something from normal distribution, multiply with sigma and Chestro. And this one as well, you got the predictor, the sigma t here, which come from random value. This is for the Euler A update. And some other multi-step update that is often used in more sophisticated sampling, like DPM++. This is like DPM++ 2M, DPM++ 2S. This is right now considered the SOTA, state of the art in stable diffusion, used in SDXL. So the idea or the main concept, let's just look at the main concept here. Okay, so instead of just CT, it maintains a small memory of previous noise. Okay, you have the latent, it maintains memory of epsilon t and epsilon t minus 1. So instead of using just one value of noise, it has two values. So it can calculate the change. right? The rate of change. Then when you're calculating CT-1 to do the reverse process, the formula use weight of combination of both previous noise and predicted noise. Nice, right? Because now you have both to form a trajectory. Right? This is standard deterministic DPM plus 2M. For the stochastic one has A here as well. So it add in Euler A to be random. All right. So this is the part that you calculate CT-1 from CT. And then you also have the error from the previous step, the memory as well, to help it in terms of learning. Think of it as having previous current latent, um, the latent before the current latent, and then doing interpolation to get the target latent, right? To something like in that way. The principle is that the predicted interpolated noise come from the weight of the two. So combine both together. Okay, so this is how the noise scheduler, different type of it work. You can see that there might be even more when you explore optimization in the noise generation. Okay. The last part here will cover the different condition beside just having text. You can perform image to image or guided generation. So instead of starting with pure noise here, in image to image, the concept is very simple. You can start with latent. You can start with the latent, right, of the image. So in the image to image, you can put x0 to encoder, right? So that's initial latent that you have. Put x during inference. Put you input x0, encode it to latent space, and then from the latent space, then you treat it as the initial. Instead of having randomly generated noise, you get it from encoding, and then you can perform DDIM and generation afterward. So just look at this image to show you the workflow. So the difference from the previous denoising step would be we have input image instead of the input latent. Instead of coming from random value or sampling, it comes from VAE encoder. Encode it down, and you have random noise. Add together, right? Mix them together, and then you have clip. Um, add to this as well, and then perform denoising. You have text to the unit condition the same way that we saw earlier. Right? We put the condition in every step of the unit, and then perform denoising until we have the final denoise version passed through VAE decoder, and then you have generated image. So that's how image to image work, right? By combining the embedding together, the latent representation of the text together with the latent representation of the encoded image. So you have image to image guided there. Right. For in painting, okay, so that's how it's done with the same latent model. You don't need to train a new model. Use the same one here. Okay. In painting, it's done through for the in painting, it's done through mask guided latent composition. So the original image will be masked. So you have mask latent. So from the image, the original image that we perform is like this. We can mask part of this. Some part set to 0, some part let it be the latent value, and then doing DDIM. And the end, just that, and add the final image out. Right. So that's part you get the original 1 minus m 1 minus mass of the original and the generated part from the mass. Right. So just that. Right? We have mass multiplied with the image. You got the mask area, then also add text here as the latent and perform denoising. And after you get final denoise, you get the generated value out there. That's how in painting. So now you can guess of the outpainting. Right? For the outpainting, we need to generate the left part and the right part. Right? So uh, everything else are the same in terms of generation. All right. Um, okay. Before we move on, let's look at um, the collab first. Let me change this to collab and take short break, and we will come back to look at SDXL. I think I already. This is the SDXL example. Oh, here, stable diffusion inference. Okay, I already run it. This is stable diffusion and exploring the hyperparameters of stable diffusion. Okay, I clone data from GitHub Convit. Let me like GitHub Convit stable diffusion. Clone it down. These are the original configuration. Install inference dependency. Sync a diffuser and transformer, accelerate, save tensor, and FTFY. And load stable diffusion 1.4 here, stable diffusion 1.4 model, and load it. It will load the data quite large though. It's 4 GB down here. Get the weight, and then this is the initialization of the grid and the generation function called generator, and then get the seed and give it with negative prompt and the prompt and number of step inference, whether you need guidance or not, the width and the height there in the generator. And this is the baseline generation. Photograph of an astronaut riding horse in the moon, on the moon, dramatic lighting, highly detailed. Set 42. Guidance 7.5, number of step 30. Okay, so this is what we got. Actually, it looks nice. It take only 6 seconds to generate this image. Then let's look further. This is to explore on the number of steps of denoising. So this example tests on 5, 10, 20, 30, 50, and 100 right, of the DDIM step to see. You can see that when you in the earlier step, obviously there's like some of the under optimized step. They are still contain noise, quite strange. Sweet spot are around here, 30, 20, and then afterwards, it start to be quite not visually improved later on. This is example of the W value, the classifier free guidance scale, right? Starting from 1 to 20 here, 1 to 20. So from 1, right? Small value means to ignore ignore the prompt. And 20, right? No guidance needed. Prompt barrier matter. 20 means strictly to the prompt. Strictly to the prompt. Well, doesn't mean that it will look nice though for this. Okay, so the best one would be about this. It still doesn't have the negative prompt here. This is the evaluation of sampler and schedulers of the this is PNDM, DDIM, Euler, Ancestral, and DPM Solver plus 2M. Each of these. Random seed, right? You get different image for random latent. negative prompt, right? We know that predicted errors equal error of negative, error of condition minus error of negative, or the contrastive between the positive and the negative. Right? This is negative, negative blurry, negative cartoon, negative contrast, and no negative. So compare all these. Um, this is negative blurry, low quality, so it would not be blur. There's still some blur here, but there's no blur here. Uh, Cartoon anime illustration, so it does look like cartoon anime. Low contrast, dull color, wash out, so it has color, even though it's on the moon somehow. Uh, Lastly, resolution, different resolution. Okay, and this is interactive. You can play with this example afterward. All right. Yeah. Let's take short breaks. I need times. And we will look at lastly on the SDXL. Right, let's take about 10 minutes break. Now is 7:37. So let's start on maybe 7:50. Right, we will look at the author stable diffusion. Right, the version that I put here is version 1.5, 1.4, right? Initial one on the papers. You can see that with this one, I still can load it on Colab and perform inference on Colab. Still fine. But for the SDXL, I cannot do that anymore. It requires quite a lot more memories, especially GPU memories to run it. So we'll look at that in after the break. Okay, let's take 10 something minutes break and continue on 7:50. All right. Okay, let me check. Okay, everything's fine. Right. Let's look at SDXL. So what I showed you earlier is XD 1.4, 1.5, and the architectures are like this. So before we move on, you may already know like this is the latent dimension, input resolution. What is clip with L14? This is the encoder part, text encoder part. Actually, it contains image encoder and text encoder that allow you to encode image and text to the latent space. This is you can search internet and you see model card explained quite well on how it works. And the Lion 5B, this is the very large data set that is used to train image. And there's like anatomy issue that was raised earlier. I think it was like one of the observation that if you want to cache generated image, you need to look at the fingers. That's come from Stable Diffusion 1.5. Okay, I want to show you the link here. This is an example of Lion 5B. It's a website of the clip with H14 Lion 2B. I think I have the earlier one. This is the open clip. This clip with large patch 14. This is from, I said it's from researcher from at OpenAI. You can use it to do zero shot because it has the best model used with L14 transform architecture as an image encoder and use mass self-attention transformer as text encoder. Hence both of these. Okay. Right. Then this is 1.4, 1.5, and then 2.0. Right, it still use the filter version of this. But it contains similar aesthetic that comparing to 1.5, a little bit higher resolution. SDXL though has different concept and it's used open clip, two open clips. That means you have two prompt that you can do the dual prompt, having the prompt one explaining something, the refiner explaining another thing. Better solution, better composition. We look at this one. The latest one, SD3, although the year is 2023, but I think the work right now is still on about this model with further further. Oh, I forgot to turn on the microphone. Since when? Do you hear I talk at all
Yeah, just a
earlier?
second. I think you hit mute for just like 5 seconds.
Yes. All right. I don't know what happened though. Oh, okay. Fine. So SDXL contains the dual clip. It has two text encoder, actually two encoder part, which allow it to fetch the encoder to the latent control to different network. One is called the base network. Another is the refiner. Okay, so SDXL use two clip encoders, the open clip with G and open clip with L here, concatenate to one another, right? And then it allows to have a richer context. Unit is larger, 2.5 billion parameters. Allow the size of 1024 times 1024. But if you look at the sea level, it's 128, right? So it expand to 2024, but inside the size of the latent vector is twice as much. Okay, but it has the base and the refiner. Right? The refiner also the work here, the base will take care of the structure. Refiner will take care of the high frequency detail and the sharpness in terms of the detail. So we would have like the two work in combination. This is the link. You can click and then it will take you to the one that I put on the collab. This is the link as well to the paper of the best model of the SDXL. Okay, this is the idea, right? Let's look at the idea and then we'll look at the implementation. The idea is that you have two encoders, text encoder 1, text encoder 2. Okay, text encoder will be concatenated. You have text encoder 2 and text encoder 1 will be concatenated to be the text input for the best model. And the text encoder 2 will be encoded through this, and then you have text encoder for encoder 2 to put into the refiner as the condition. So it means that you can have two versions of the prompt. They can be the same, but that would be repeating the same thing, or they can be different, like close-up shot, shallow depth of field, and the style. This should be put in the refiner, and the composition should be put in the main text, main prompt. Okay, this is the composition of SDXL. And SDXL works similarly. You have noise from the latent, you have base model, then denoising, you have condition latent, denoising process and step. Then the condition latent is put to the refiner and then perform denoising again, and then pass through VAE decoder to get the end here. Okay, so this is the SDXL architecture. Okay, so I have some example that I ran from the collab. This is from the prompt, a majestic snow leopard on a rocky Himalayan ridge at sunset. And still positive in the same way, using the same prompt, photorealistic, sharp focus, dramatic golden hour. Right? Then for the negative, blurry, low quality, deformed, extra limb, cartoon. Right? So base only, it looks on the left hand side. So still okay, right? Looks great actually. But if you look at the base plus refiner, you can see obviously if you look at the fur, right, and also high frequency detail and the eyes here. Look at the eyes. Look at the parts around the nose here, around the nose area. Right, you can see the difference that are quite obvious, especially in terms of the realistic and the detail. Look at the part of the rock here and the part of the rock here as well. This is latent handoff. That means we put the latent to the refiner. This part is putting the image to the refiner. Okay, so putting image to refiner results in the image that looks like this. Very similar though, as you can see. All right, so let's look at some adjustment for the SDXL. It has the control between the portion that will be optimized by the base and the portion that will be generated by not optimized. Sorry, that will be generated by base and the part that will be generated by refiner. If we were to set it to 0.5, it will look like this. Right? 0.5 would be 50% of the base, and refiner has 50%, meaning that refiner will have to take care of some of the detail as well. That's the reason that you see here that the refiner adds some detail, the refiner adds some detail. Right? It adds some detail that's not in the base here because it's like 50 and 50 between the two. If it's base 80, refiner the rest 20, it will look like the base but with more detail. And this is the base and with some more detail, right? That adding into that. So this is a split sweep that can be put into the generation. It will the final latent partly will come from the base and partly will come from on the refiner and then add together to form the final latent. SDXL also allow you to get one with high and low aesthetic score. This is the resulting of the low aesthetic score, very bad image, and high aesthetic score, which you get very cool, fluffy fur there. And because SDXL has dual clip text encoder, you can have the same encoder look like that, or you can have like one encoder to be a snow leopard on Himalayan ridge, and another to be oil painting in the style of Caspar David British romantic painterly, and you get the result. This is like the painting. So the first one is fetch. Actually, both here are fetched to the main image, right? You can see the concatenation between both prompt, both clip to the main image, and the second one is only put through the refiner. So refiner receive only the second one. This as well, it has the second part as cinematic, dramatic, golden hour lighting, ultra detailed photographic style, and the first one combined looks like this. Right? So this is the dual text encoder. All right. Further, SDXL has the multimodal capability. This is not SDXL, sorry. This is SD3, Stable Diffusion 3. It has rectified flow and multimodal, right? Diffusion transformer, MMDIT. So the aim is to, and it has 3 text encoder, and the idea here is to allow the model to be a multimodal. Right? So you have a combination of latent, and then because I'm not going to go to detail here, so just to show you that it contains a lot more complicated generation, and the focus then would be in terms of the multimodal diffusion transformer. But I haven't seen the model that coming out from SD3 yet. But there are papers that you can look for into that. Right. So comparing in terms of benchmark, VRAM use and quality, for stable diffusion, you need at least 4 GB in inferencing. That's the resolution of 512 and 20 steps. On 3090, it takes 3 seconds. On 800, it takes 1.5. The FID score is 15. Okay, so for SDXL based refiner, it's better. Okay, but it needs more RAM. It takes more time, and if you use Colab, it takes a lot more time. Okay. Lastly, I want to put it here. Lastly, with the ability to generate image, it comes with responsibility. Okay. Firstly, the data, the model that we discussed today is those models are trained on Lion 5B. So it contains internet bias of Lion 5B. Okay, and it overrepresents Western aesthetics. If you ask for Lai Thai, for the detail in Thai, it wouldn't know, right? There are a lot of underrepresentation there. And you get stereotypic output, gender, race, profession, religion there. And the mitigation for the bias would be to curate and fine-tuning the process. Second issues in ethical consideration that you should think about is that surely you can generate face, you can generate non-consensual image from the generation, and it can be used for political misinformation, synthetic media, right? Or NSFW as well. You can put safe filter into that. And actually, if you look at a lot of AI providers, they put in the safe filter to filter the output so that it would not be NSFW, right? For some. And also the Stable Diffusion Creative ML license prohibit harmful application. So be careful. You may get sued if you use it in a bad way. Lastly, Lion 5B scrape copyright web image without consent. So that's that problem. And with the latest one, what is the name? The name of the Do you remember? Anyone remember the generated one, Pikachu, and the realistic one? What is the name of the model from China? Anyone remember? What is the name of that model that is very realistic? That they use quite a lot to generate the video nowadays. What is that name? Not once, not Kling. Quite not popular per se, but quite widespread. People use it quite a lot. I don't remember the name though. What is that name? It sparked a concern. People said that you can just use it. You don't have to pay $3 million to make video. You can just do it in 10 seconds. But you use face of authors without permission. But I don't remember the name of that model from. Anyone remember? It's just I think it was just 3 or 4 months ago. It's the generative AI video model quite popular in on X. Let me check. What is the name? What is that name? That they use the data, the face data from Hollywood. Yeah, I should search that. Hollywood. From Hollywood, actor and actress. Sorry. Still, don't remember the name though. If I can remember it more or less, I will tell you. I don't remember.
Is it sea dance?
Yeah. Seed dance, right? The seed dance. Right. It sparked the discussion quite a lot because while the models looks cool, but the models itself use data from actors without their consent. Right? So that's the problem. And also use the content that are owned by authors without the consent as well. Okay, so there are multiple lawsuits from artists. Problem of style mimicry, uh, watermarking, and tracking has been used as solution, but not successful though. So that means you have to remember that great power comes with great responsibility. You can actually, if you use it right now, you can generate the data that quite detailed with just a few line of code, even use Colab. Right? I'm going to show you here. Without really have to use the Open Web UI or Comfy UI at all. You can do that as well. This is XDXL. Okay, let's just look at part of the inference that's because we load the model from the repo and some memory management, loading the best model, diffusion pipeline from the pre-trained, stable diffusion XL base 1.0, and this is FT16, quite detailed. This is the stable diffusion XL refiner, and then this is 3 inference model, right? The prompt negative, then during inference base only, you get MIG base, the base model, and then save the image from that. The latent line of putting output type as latent, then I put the latent to be the input, the image of the other one, and then get the final output, and then here you get the latent. Use the same prompt and negative. Lastly, this is image handoff. Put the image here. The change in the hyperparameter, there's the split. You can put it into the split. Okay, for between the base and refiner. This is a split S, right? The denoising start S. So denoising end at S and the denoising start here. So it tells you the proportion that you will let the refiner work to a certain portion. This is aesthetic score, specify aesthetic score. I'll just skip this. Let's look at the dual text encoder, the cool one. Here you have the first each one as a tuple. Then the first one come to the prompt P1, the second one come to the prompt P2, and refine as well, different prompt, and then you get the result there. All right. Okay, I already upload it to LEB2. So if you want to play around, you can try. You can try to add Latin together. That would be interesting. I haven't shown you here image to image. Oh, you can try the image to image with stable diffusion, encoding one image to be input of another one. You can play around with the SDXL here as well if you want. All right. Okay. Right. So those are the part that I will cover, part related to the concept of stable diffusion, latent diffusion models, and extensions from 1.5 to XL. Right? You can see the change there. You can actually run all of this in the no code style using Comfy UI. Which I'm not going to show you. At first, I thought I'm going to show you as well. Let me check if I prepare some example. If not, then maybe not. Maybe I will let Y talk about the lab if you have that. Okay, ครับ Y you can share.
Okay. Okay. Let me so let me share my screen. Okay, so the resolution of my screen will look a little bit weird though because I use ultra wide now, but that's okay. And for the lab, for this lab, it will be the lab 8 on diffusion model, which includes both the DDPM from the previous lecture and the stable diffusion model from this lecture. So it will be split it into two parts. Part 1 is I want you to train the DDPM from scratch using the code that I uploaded in the previous lecture, and use this one, the doc image dataset, to train your DDPM. And for the part 2, before we are going to the detail of part 2, I want to demonstrate on how you can fine tune the diffusion model using LoRa. So this one I have the baseline model from Ajahn Yai's code in LEB2, and this one actually is perform pretty good already, but you can fine tune the model to for it to be suitable for your task, for your data set. So let's quickly look through this notebook. Oh, this one is already in the lab 8 diffusion model here. You can find all the dataset files and the notebook here. Okay, so first of all, let's load our baseline model and then give it some prompt and generate some image to get baseline generation of the model. So this one is from Ajahn Yai's code, as I said earlier. This one I use the stable diffusion V14. Okay, now the model is loaded. If you run this block of code for the first time, it will take quite some time because it needs to like load the pre-trained weight from the internet. If I remember correctly, this model is around 4 gigabytes. in total. So pretty big. And for the next one is just the helper function to plot the image and generate the image according to the prompt and other parameters. And let's get some baseline image generation. So for this one, I want it to generate an image of a camellia flower. And it is this one. So it looked quite nice, but it missed some information that I give in the prompt, like using shallow depth of field is okay, but I want it to use the soft low key light, which it missed in this case, but that's okay. And from now we can fine tune this model using the LoRa technique that we learned in the previous lecture. So we are gonna do the similar step as in fine tuning just a normal transformer model. So this one we just set up the LoRa. So we are going to use the same library that we used last time called PEFT, performance parameter efficient fine tuning. And we set up the LoRa. We use the rank of the LoRa matrix as 8 and the scaling factor of 16 init weight by Gaussian, and we are gonna target the Q, K, and V and out module of the unit in this diffusion model. So how you get this one? You just take a look inside the model that you are going to fine tune, which in this one is the model called pipe. If you just print out this model, you can see that it contains a lot of modules, submodules. We are going to target the module inside the unit here. So if we go inside the unit, you can see that it contains a lot of layers, a lot of blocks, and just like in doing LoRa with transformers, we are going to target the Q, K, and V layer of the module. So we are going to target this one to Q, K, V, and out. And because we are going to target just a small amount of the parameters, we are going to freeze the weight of other components that will not be trained in LoRa training, which is the other parameters of UNet, other parameters of VAE, other parameters of text encoder. We are going to set the required scratch to false. By setting this, during the backpropagation process, the weight of these modules will not be updated. And then we attach the LoRa adapter to the model. So you can see that out of 800 million parameters, we are going to train just 1.5, 1.6 millions of them, which is less than 1%. And next up is the dataset. For this demo, I will use just one image to fine tune the model. In reality, you would have a lot of image dataset to like fine tune the model to be able to work in your field. But this one is just for the demo, so I just used one image, which is this one. This one is the pink camellia flowers with like soft lighting and shallow depth of field, pretty low key light. So what I'm gonna do here is to read this image and then give it a prompt or the description of the image so that the diffusion model can learn that this image contains a pink camellia. To the left from the main flower there is a blooming bud, and then this use a shallow depth of field, soft low key light. Okay, so read this one and then transform it into a tensor. And then we are going to train this LoRa. So we are going to set the mode of the model, the LoRa model, to train mode, and then we are gonna train this for 1,000 epoch. Because the image here is being resized to 512 pixels by 512 pixels, and it's just one image, so I can use like crazy number of epoch here. But if you are going to do it with the real world samples, say you may have like 10,000 of images, then maybe you have to like tweak the parameters, the training parameters for a bit. Okay, and then we are going to fine tune this one. It takes some time, but you will see the result that if I give it the same prompt again, now it will generate the image closer to the examples that I gave it in the LoRa training.
Cool. Okay. While we are waiting for the step, let me quickly show you this one. Let me quickly show you this. Okay. This is Comfy UI. I'm not sure if well, using the SDXL base 1.0, I'm not sure if you will so it looks, I don't know if you can call this simpler from the SDXL that I show you in the code, but it contains pretty much the same thing. Pretty much, you have the load checkpoint, which load model. You have clip encoder, positive and negative. Prompt put to clip text encoder, which then put to the sampler. Okay, denoising. And then you have the refiner, load the refiner model, and this add from the same one. Okay. And you got the VAE at the end. Because this is text to image, so there aren't any encoder. If you want the image to image, you need to put in the VAE encoder to that. So this will encode. For this one, it will decode from the latent, right, from the sampler, and then decode to the image to save it. Right. This is the evening sunset scenery, blue sky nature, glass bottle with galaxy in it. Very nice. Okay. All right. So this is a workflow light. It's called Comfy UI. You can do the same thing as in what we did with the code, but with the workflow instead. However, if you want to perform a lot more complicated or more combination, adjusting the flow, mixing the latent, you can do that, but it's complicated to do it here. Comparing to code, you can just add the latent together, for example, or interpolate them together. So yeah, I just want to show you this one. It's really nice. I'm not sure if I should call it easy to use or not, because for me it's not that easy to use. But once you get the workflow set up, if you want to do it in a larger scale or to adjust something, it's quite okay, especially if you want to try multiple especially the model without really have to write the programming. But with programming, like what I show you, you can do quite a lot more. Right now we have combining it with LoRa as well. Okay, I suppose that it's almost done.
Yeah, it's done now.
Okay,
So
let's
let me
continue.
share this one. And after the model finished the LoRa fine tuning, now we can like generate the image from the fine tuning model. So right now we are going to set the mode of this model to eval, which means we are going to use this one as a generator, and then we give it a prompt, which is the same prompt that we used in LoRa training. And then let's see the result. Oops, why is okay. Okay, you may see the resemblance of this one to the example image that I give to LoRa training. So the quality might be not that great, but you can see that it captures some of the details of the flowers, of the leaves, of the branches, and the lightings. If we give it more training samples and train for more epoch, I think the result would be better.
Right. Usually you would need say hundreds of samples and annotated data to train LoRa to make it work effectively. Okay. So the work that they have to do would be to explore this, right?
Yes. So the first part I already explained it to you to just train the DDPM using this docs image dataset. And for the second part is to fine-tune the diffusion model using another dataset called the pixel desert, this one. So in this one, we have image of a desert, quite a lot of them. I think it contains around 200 something image of the desert, like this one here. And we have not the prompt, but the description of this image in this file, pixel desert CSV. If you read this one into a data frame, you will find this. It contains 3 columns. The first one is the file name, which correspond to the file name in the desert folder. The second column is the title of the image, which gives a broad description of the image. And the third one is the text, which contains the text about everything that is present in the image. So I want you to use these 2 columns, combine it as a prompt for training, for fine-tuning the diffusion model. All right.
All right. Sounds challenging. So this might take more than 1 week.
Yes, I will give you guys 2 weeks for this because I think the next Monday is their national holiday, right?
Right. So there will not be no class on the next Monday.
Yeah, so this one we'll do on 11th of May.
Right. And actually based on the topics of the thing that we can really train, it would be almost at the end of the thing that we can train, right? After this, there will be the topics of actually there are 3 topics left, but I don't know whether we would have enough time for that or not. Let me check the schedule again because we will have the project presentation on the 18th. Is that right? Or the exam? Anyone? So if I remember correctly, we would have project presentation first and the exam later. Is that right? Everyone. So is that what we agree on last time? So the project presentation will be on, let me check. The project presentation will be on the 18th, right? On the 18th. And then the final exam will be on the 25th. Am I right, or did I mess up with the date? Yes, yes. Thank you. Thank you. Oh, actually, I can refer to what we discussed back then as well. Okay, thank you anyway. Thank you, Ratadon. 18 presentation, 25 final exam. So we have just another lecture that we can cover on the 11th. And the topic that I wish to cover is actually the ethical aspects of generative AI. Although I'm not sure if we can go into detail on the discussion or somewhat. So since we focus the course on the technical, let's stick with the technical then. For now, we have seen text generation, image generation on different way. For the last lecture, let's look at the multimodal. All right, the multimodal generative AI and modern architecture, right, to see what's out there. We look at a bunch of papers that could shed like the light of the new generative models. All right. So that means there shouldn't be any assignment on the last lecture. So this would be the last assignment. Great. It's completed before the term project. Term project is on 18. Okay. So you can, as I said, you can choose to do whatever. Actually, some of my assignments are already quite difficult to be at the level, almost at the level of project. Maybe you can do better actually for the project because why ask you to do quite specific tasks. You can generalize from that to have very interesting term project, and then we can see about that. Okay. Right. Any question that you would like to ask about the work? As you can see, we try to select the example that is runnable on Colab for you. Okay, instead of relying on the GPU alone. Right? So maybe your term project can be experiment. That's fine. Latent representation experiment. That would be fun. Okay, it doesn't have to be the generative model. It can be experiment about the model. It can be some study. It can be testing, mixing the model together. Right? So those would be quite interesting. Or try to do the image to image style transfer. Right? So there are quite a number of them that you can try on. Okay. Any question? If you want to discuss about either the technical detail or the theoretical detail with me or Y, please send us the message. Okay, we will get back to you, especially if you want to confirm about the project, whether it's okay, whether you should expand more. Try to send us message as soon as you can. Before the project day is not good enough for that. All right. So, okay. Any question that you have? If not, then we will close the session. Okay. Thank you, everyone, for joining. And there's no class next week. It's holiday. We will see each other on the 11th. All right. On the last lecture of generative AI. Have a good night, everyone. Goodbye.